So an example of Newton's second law with components. So doing a little bit of SOHCAHTOA stuff in a force problem going lefty-righty. So on this question, they tell us that the mass of the car is 250 or pardon me, where did 250 come from? They tell us the mass of the car is 1,500 kilograms at an angle, being pulled at an angle of 20 degrees. Frictional force is 320 newtons. What's the tension in the rope? So if I start off with the free body diagram, I'm not worried about the car, the entirety of the car rotating. The wheels will spin, but the mass of the wheels compared to the mass of the vehicle, pretty small. So I'm not concerned about that. So if I look at a free body diagram, they've done a nice job of circling this for us. So we know, yeah, the Earth is pulling it down. There's a gravitational force, Earth on the car. There's a normal force of the ground on the car pushing up, also Earth on car. There's this frictional force as this thing is going, pushing to the left. Frictional force, road on car, Earth on car. And then the force moving this thing forward is this force of tension of that rope on the car. That angle, 20 degrees. All right. So if we want to find this force of tension on the car, let's see. I'm going to go through and set up a list of things that we know. I'm going to say in the x direction, we know a few things. We know the force of friction is 320 newtons, and that's to the left. So I'm going to take a second and say, hey, to the right is positive, to the left is negative. That makes this 320 newtons negative. Lefty-righty, we don't have any other values actually given to us, but there is that force of tension, rope on the car, that does have an x component. We don't know what that is immediately right now, but we know that that does exist. There is the x component of the force that's acting in this direction. In the y direction, they didn't give us anything directly there. So we can play that same game with the force of tension rope on the car y direction. There is a y component to that. We know that there is also a normal force that the Earth exerts on the car. We don't know what that is immediately right now. And then, so we have our set of x direction stuff, we have our set of y direction stuff, then we have some tweeners, some things that are just kind of universally true. Neither x nor y. We know that the mass is 1,500 kilograms. We know that the angle is 20 degrees. So with that, that gives us a few other things as well. So if we're going to try to find the force of tension, I'm going to use this tweener space to also say, hey, this is the force that we're actually looking for. That T should be up a little bit more. I don't know, this eraser sometimes is sketchy. That worked okay. So that force of tension is up at an angle. Then I can say, hey, there is, I just hit something. There is this force of tension, rope on the car, X component, and this force of tension, rope on the car, Y component. So those forces all exist, or components of forces all exist. We know that degree, that angle, is 20 degrees. So if I'm going to try to find, if my big go-to is to try to make sure I can find the tension force that the rope exerts on the car, that's our big go-to. Well, if I can find the Y component, I know I've got an angle, and I could use SOHCAHTOA to find the hypotenuse. If I find the x component, I can use SOHCAHTOA, and I can find the hypotenuse. So right now, I'm going to say, hey, what do I know more about? Do I know more about the x direction stuff or the y direction stuff? And, well, I know at the very least that I have this frictional force is 320 to the left. So I'm going to use the x direction stuff to try to work this problem. Another thing worth noting here in the givens, I wasn't as careful as I should. They say steady speed. So that means that the acceleration is 0, and that means that our total force in the x direction is also 0. So now, when I'm looking at the x direction for this car, I can say, hey, oh, what happened there? Get rid of that. Get rid of that. I can say the sum of the forces on the car in the x direction are this frictional force and the x component of tension. So I can say it's frictional force, rope on car, plus tension force. Oops, sorry, rope on car. Bleh. I'm becoming a little concerned about the space that I've got, and I'm writing these things down in a way different from past, so my mind's running a little bit. Frictional force, earth on car, and tension force, rope on car, but not the whole thing, the x component. And that equals, that's the sum of the forces, and that also equals ma. So I can say this plus this equals ma. And once we just noticed up here, hey, it says steady speed, that means that the acceleration is 0. That means this is 0. So this force plus this force equals 0. And we know this is to the left and this is to the right. There we go. So now at this point, I can isolate this, and I can say, hey, the tension force, rope on the car, x direction, equals, take this, move it to the other side, equals the frictional force, earth on the car. So, and they told us that frictional force was 320 newtons. And now remember, these red positives and negatives are telling me the directions that I have. So this actual 320 is the actual x component of that force of the rope on the car. So we're just about there. Now to find the actual force that the rope exerts on the car, I can say, hey, this, like drawn above, is the force I'm trying to find. This angle is 20 degrees, and this we know to be 320 newtons. This y component we don't know. It doesn't ask us to find. We could if we wanted to, but no need. So now here we're trying to find this hypotenuse, the actual resultant force, the actual force that the rope exerts on the car, and we know the x component is that. So now we're back to thinking about the sine of the angle is opposite over hypotenuse. The cosine of the angle is the adjacent over the hypotenuse, or the tangent of the angle is opposite over adjacent. Well, the angle is 20. We know the x component. That side is adjacent to our angle. So we're looking at one of these two. And the other thing we know is, or we're looking for, is the force of tension. So that's the hypotenuse. So we're really looking at cosine. And so I'm going to put this cosine equation into physics terms. Instead of saying A or adjacent, I can say the tension force rope on car x component over, and instead of hypotenuse, I can say, hey, the thing I'm actually looking for is this. Now I want to get this by itself, so I'm going to multiply both sides by that. And now I get this. And I want to get that tension force on its own. So now I'm going to divide both sides by cosine theta just to get that out of the way. And now I get this. And if we put the numbers in, then that's 320 newtons divided by the cosine of, that was 20 degrees. And plug that into your calculator, and you get what you get, and we should be good. So that ends up being a long bit of stuff, but we should be okay with what we've got there. Looking at my calculator, I get an answer of roughly 340, and then there's a bunch of decimals. I'm going to stop at the 0.5. And if we're going to put a direction on it, now remember the direction for this force would not be positive or negative. That's not the direction, because remember this thing was going up at an angle. So if we were to include the direction, it would be, oh, what's happening there? It would be maybe an unnecessary additional step, because the problem tells us that this is at 20 degrees above the horizontal. But that's one of the ways to do it. And that's that. I'll see if I can stop this, and there you go.